I'm very glad to be here. Good morning, everyone. I'm going to give a talk with such a lengthy title. I only realized this now that I see it in big. So the aim of this talk is to provide you with a kind of high-level picture of how we see in IQM our roadmap towards fault tolerance. And I'm going to be talking about the milestones that we have, also the challenges. And by the end of the talk, I will also be discussing what will be or the impact of quantum advantage when talking about real market. So first, I would like to say a couple of words about IQM. For those of you that do not know us, we are a company working on fabricating quantum computers based on superconducting qubits. And our mission is to build world-leading quantum computers for the well-being of humankind. The first time I heard this lemma, I was a little bit skeptical. I thought it was too grandiose, but I think nowadays it's very important that we at least have this mission in mind. So we are more than 300 experts currently. Almost half of us have PhDs, so I think it's very interesting, kind of enriching atmosphere. We have more than 50 nationalities, so we are very proud of our diversity. We have our own fabrication and assembly line, which I think is the only private-owned assembly line for superconductors in Europe. And we have built more than 30 full systems, and we are delivering them on premises in high-performance supercomputing centers like LRC or BTT in Finland. And we are currently building in our fabrication 150 qubit chips, while 54 qubit systems are already being offered in cloud. So this is the content of the talk. First, I will draw more or less the high-level vision of our roadmap and how we plan to basically what would be the timeline for going from the noise intermediate scale quantum era to fault tolerance. Then I will go to the second part of the talk, which will be mostly about the challenges and the strategy and the different milestones. And by the end, I will say a couple of words about how I currently foresee the impact of quantum advantage, going a little bit in more detail, but still high level. OK, so 1 year ago, in November 24, we were publishing this roadmap. At least this is the hardware part of it. You can see already identify some elements. Let's see if the laser is working, that are already in the cloud. This is the 54 qubit chip, and this is the one that is being built in our labs. And as you know, we are dealing with two different kinds of topologies. One that we call crystal, that is basically a square lattice arrangement of superconducting qubits. And then we are also working with this star topology, which is based on having these central elements here in the middle that are acting as a hub to which multiple qubits are connected. And I will show you in the second part of the talk how is this relevant when it comes to implementing high-performance quantum error correction codes. So the important part here is that if you look at the number of physical qubits here, there is a huge jump from the NISQ era to the early quantum error correction demonstrators. And we are still talking about demonstrators because the number of logical qubits that they will have will not be sufficient to be able to perform industrial relevant quantum computation. So this will come when we have hundreds of logical qubits already in this era of fault tolerance. So we have a long roadmap ahead, but still just a couple of words about the NISQ era, where we are in, sorry, as a community. Within this era, how do we tackle the challenge of noise? As you know, most of the community members are using a technique which is called quantum error mitigation, which is based on using some kind of redundancy in the number of times the circuit or similar circuits are repeated, are run. And of course, because of this extra number of times, there is an overhead in terms of time, which means that if you are running a circuit that would last, for instance, a couple of minutes, then you need to run it for a day if you want to, for instance, make use of 100 qubits or dozens of qubits. or utility qubits. So this is kind of like a bit the condition that you need to take into account for error mitigation, that the scaling of this overhead in time is exponential with the number of qubits, which means that this technique is going to be pretty much restricted to this NISQ era. So you're not going to be able to use more than 100-something physical qubits for your utility algorithms. It's not working right. My hair now is going to be crazy. Sorry. Okay. Okay, well, now it's better? Yeah, sorry. It was a bit, I was also noticing something, but. Okay, so this is a bit the limitation that we are dealing with. Okay. Did I do something wrong? No? Okay. Okay, okay. I don't know what happened. Okay, so good starting. We were only in error mitigation. By the way, of course, you can, I don't know how is, Robert, if people can ask questions on the fly, or is it at the last minute after I finish? I don't know how is this better arranged. But in general, I'm happy if people simply ask questions.
No, it was just a black slide.
Oh. So it was my fault. Okay, good. Sorry. Black slide. Okay. So here I just wanted to show you a technique that has been developed actually in the team of Adrian Auer, who is somewhere in the public. Amin Hossein-Kani is the first author. This is, for instance, one of the most advanced error mitigation techniques that we have developed. It's called noise-robust estimation. And here you can see a test of this error mitigation technique with Garnet, which has 20 qubits. And it's dealing with an algorithm to calculate ground state energy with QAOA for this transverse field Ising model. And the technique is based on, just like a zero noise extrapolation, on making measurements of the quantum mean value when you multiply the noise in the circuit twice, 3 times, 4 times, etc. Here is for the target circuit, and here is for one of these extra circuits that you generate that are called noise canceling circuits. And basically here you can see the comparison between NRE technique, this new technique, in terms of the residual error with respect to other state-of-the-art techniques. So the error is pretty much reduced. But as I said before, the limitation here is very clear, is that basically you cannot go beyond using 100-something physical qubits for your calculations. And also circuit depths cannot be very, very, very large. So then in the second part of the roadmap, of course, like the rest of the community, we want to use these quantum error correction techniques, which are based also on this idea of redundancy. But here, the redundancy comes in play by considering extra physical qubits to implement a single logical qubit that reduces the error rate from around 3 or 3 up to 3.59 into an error rate of 10 over minus 8, meaning 1 error every 10 over minus 8 calculations. And by the way, this is the minimal logical error rate that you need to attain in order to have, for instance, chemical accuracy for computing molecular dynamics in an industrially relevant problem. So this is kind of the minimal. 10 over minus 12 would be what you would be needing if you wanted to use quantum to decrypt for decrypting cryptographic codes. So this is a bit the target, and as you can see, there is a large gap between the utility era where we are in to the first quantum computer that will have sufficient number of logical qubits to be used for industrial usage. So just to give you an idea of what this means, you have to think about a logarithmic representation in the number of physical qubits. These are all our NISQ systems. This is the 2-qubit gate fidelities that we are attaining. The whole community is also clustering their points around here. And if you want to use the surface code, this means that you need to have 200 logical qubits, have around 100,000 physical qubits. Nevertheless, if you use quantum LDPC codes that are quantum error correction codes with a higher encoding rate, this can be reduced significantly. Specifically, to achieve 200 logical qubits, you just need to have 20,000 physical qubits. And the price to pay is that you need to have a lot of connectivity between the qubits, the physical qubits in your QPU. So you need them to be non-locally connected, which means that if you want to implement this kind of codes in a square lattice, you need to produce a lot of swap operations to be able to connect this guy with this guy, and in general, qubits that are not physically connected with each other. And that's the reason why the strategy that I will describe you in the second part of the talk is pretty much about coming up with new architectures or topologies that natively implement this large connectivity that is required for quantum LDPC codes. But before going there, I just want to give you a bit of an overview of, yeah?
So does this mean that you need something just three-dimensional? Because the hardware needs to be something just three-dimensional?
Ideally, yes. For instance, if you were able to have all-to-all connectivity, that would be super. But
It would be very happy.
Right. So in principle, with superconducting qubits, what some companies are doing, some of our competitors, they are considering a square lattice with 2 long-range connectors per plaquette, which are kind of enabling this large connectivity that is required for quantum LDPC. This is what other companies are considering. In our case, as you will see in a couple of minutes, we are implementing an architecture that contains a lot of connections between the qubits. Yes.
So from a purely just as a mathematical object, graph theory,
Yes.
Have you heard of things like expanded graphs?
Expanded graphs.
Yeah. So graphs where you can quickly move from one part of the graph to another part of the graph, but the number of connections that you have are not very high.
Okay. So maybe this is something, I have not heard about this, but maybe we can catch up later. Thank you. Very good, thank you. So this is a bit of an overview of the stack that we are working on in IQM. So we are doing everything that comes from QPU design till the algorithm level, including quantum error correction. And there are plenty of challenges in order to scale up to a system that has quantum advantage, this fault-tolerant era. So first, we have to come up with a design process that contains all the elements of advantage, in particular enables to design the blueprints for chips that enable these strongly connected architectures and possibly some extra long-range connectors. Then we need to work on the fidelities at the QPU level so that we meet the quantum error correction requirements. The more we go towards 3.59s, the better, because then this means that we can have a higher encoding rate. And when it comes to fabrication, of course, there are huge challenges ahead. We have to produce vertical connectivity to enhance signal routing and tiling solutions, tile qualification, etc. Full system integration is mostly challenging now due to the electronic part because of the need to have very fast operating electronics to perform quantum error correction cycles. Auto-calibration, of course, needs to be ready for these large systems. You need to have a fault-tolerant software stack and quantum error correction software stack. And of course, then, as I will explain you in a minute, what is very core for us in IQM strategically is to have a very strong connection between these two elements here, the design, the fabrication, and the error correction theory. And this is a bit what I wanted to explain in a bit more detail. The fact that one core aspect of our strategy is that we are working on this quantum error correction code engineering. So our goal is to reach codes that have 10 times better performance per physical qubit than standard surface code. This is super ambitious, but of course that would mean that we can, for instance, diminish the requirement in the number of physical qubits that you need to implement a logical qubit. And this is a target that is kind of increasingly being achieved by our quantum error correction team with Francisco Repson leading. So here is a recent result by Vincent and from the team of Francisco and other co-authors. What they did, they created a new family of quantum LDPC codes that are called tile codes. And these are very interesting. Why? Because they have open boundary conditions. Why is this interesting? Because before those quantum LDPC codes used to have be toric codes. So meaning that if you want to implement them in superconducting qubits, you needed to connect all qubits in the borders with the ones in the other corner and so on. So you need to really produce these long-range connectors between the qubits in the limits. Here, this is solved. So now the codes are truncated, which enable their implementation in this kind of chips without having to connect these guys with these guys. They still have a very high efficiency, very importantly, because they don't have this toric code topology. They enable dynamical operations. So you can move the patches, you can shrink them and stretch them. Similar to surface code, which means that you can perform, for instance, lattice surgery in order to produce fault-tolerant gates. So this is now what is in progress in the team. They are working on creating fault-tolerant gates with this kind of codes. Another nice property is that they have a nice scaling. Nice, what does it mean? Nice here is that if you want to increase, let's say you have a patch of qubits, and which corresponds to a certain code distance and the implementation of a number of logical qubits. And let's assume now that you want to increase the code distance or the number of logical qubits. Well, you just need to increase the lattice, grow it exactly as it is, like copy-paste, and you will be able to achieve this property. It looks very obvious, but it's not a property that previous quantum LDPC codes had, where you actually had to make reconfigurations and changes in the topology if you wanted to increase the code distance or the number of logical qubits. So all these look good, but of course, again, there are lots of challenges ahead. And one of them is precisely about the gates, because a good disclaimer is that this improvement in the high efficiency is for memory qubits, for memory logical qubits. When you increase the overhead that you need to add when considering gates, then the increase in performance with respect to the surface code is not so large. And that's why the team is now working precisely on building quantum LDPC advanced logical gates. So this is still work in progress, also for the whole community. So the second pillar of our strategy is that we co-design the architecture or the topology of the qubits in a way that they can implement these families of codes, these quantum LDPC codes, efficiently. Efficiently meaning that you don't need to add a lot of swap gates. So here you can see that this star topology that I was describing at the beginning in this big slide with the roadmap is now forming a more complex structure where the central element, you can recognize it here. It can be actually a resonator, but it can also be a qubit. But the important thing is that it's acting like a hub to which many multiple qubits are connected. And the nice thing about this architecture, this structure, is that it has an optimal trade-off between parallelism and in-plane connectivity. So it's kind of like ideal to implement this kind of codes, even though we still think we need to add some semi-long range connectors here and there. We are still seeing how to make it a bit more connected in order to reach more powerful families of quantum LDPC codes. But still, if you're curious, you can check out our first experimental results with this kind of architectures. This architecture that is in cloud that contains 6 qubits connected to a resonator. You can check out this reference from the teams where they were doing an error detection experiment with up to 3/9 of fidelities, which is a good benchmark because it's similar to previous results with neutral atoms. So we are, of course, having to increase the fidelities of these operations because having added the central element, being a resonator and having a lot of qubits connected to it, this produces more difficulties when it comes to calibrating these kind of gates, and this is still in progress. Another part of the stack, which is very relevant for the fault-tolerant roadmap, is this part that has to do with the electronics, the quantum error correction software stack, and of course, again, the error correction theory. And here, what I want to introduce to you is 2 visions on the error correction elements. One is this theoretical quantum error correction stack, all the elements that in theory are needed to implement error correction. And in the next slide, I will add a more dynamical picture of how does error correction works. So the first one thing that I wanted to mention here is that for surface code, all elements of the stack are figured out. So specifically, we already have even experiments on memory qubits, Clifford operations, non-Clifford operations that makes the full computation universal. This is needed for universal quantum computation, but it, of course, requires to have some extra gates with respect to the Clifford ones. And then you need to have a transpiler, which is basically adding the adaptation of the quantum algorithm to native gates, just like in NISQ era. But it also is adding, for the error correction case, the quantum error correction scaffold, which is basically the set of syndrome qubits. So you know that in error correction you have data qubits, where your logical qubits are encoded, and also syndrome qubits, where you make the measurements that tell you if an error has been made or not. All the gates corresponding to QEC cycles and the different measurements that you have to do on the syndrome qubits to keep track of the errors. So the difficulty for quantum LDPC codes is that these elements are still under construction. And this is what the whole community is working on currently. In our teams, we are working still at this level, but we are advancing pretty fast. This is the early memory experiment that I was describing before. For one case system, we expect to test at least Clifford operations, hopefully with quantum LDPC codes. And at the latest, with the 5,000 physical qubit systems, we expect to have the full quantum error correction stack being implemented. So this is a bit the combination between this theoretical vision of the QEC stack and our roadmap, our program. So, but let me tell you a little bit, a very naive, innocent version of how does a quantum error correction cycle works. So far, I've been talking about QPU and the relationship with the quantum error correction theory stack, how the topology of the QPU is super relevant for this implementation of codes. But now imagine that we have a user that is wanting to implement a fault-tolerant algorithm or a quantum error correction-ready algorithm, like Grover or, I don't know, quantum phase estimation. And so what is going to happen is that the transpiler is going to mix the theory stack elements with the quantum algorithm to produce this QEC-ready program that contains this translation into native gates, plus this QEC scaffold, namely all the different elements that are needed for implementing the quantum error correction cycles. So then what happens is that this is sent into a firmware layer that is kind of going to produce high-level management, or this is kind of like an orchestrator layer that is taking this ready program and producing a scheduling of all the different gates that correspond to the quantum error correction cycles. And this is going to be communicating the information to a decoder. And I will show you in a minute. Actually, the decoder is receiving measurements from the syndrome qubits and later on the data qubits when the algorithm is finished from the detectors and actuators that are receiving the information from the QPU. This guy, the QEC cycle manager, is simply scheduling in a lower level the communication of the signals to the QPU when the gates need to occur, and also receiving through the detectors the readout signals. So this is kind of like a very naive scheme. Finally, of course, the user receives from the decoder or from some of the elements here the result of the algorithm. But the overall goal here is that the coherence time that in general for superconducting qubits is of the order of microseconds is extended to seconds so that you can actually run a lengthy algorithm. And you have to think when it comes to quantum error correction cycles that these are continuous cycles that are being run so that errors are detected and corrected. And there are around of tens of quantum error correction cycles per logical operation. And when you think about the coherence time being of the order of tens of microseconds or maybe 100 microseconds, this means that the quantum error correction cycle has to last 1 microsecond, which means that they need to be very quickly operated with the electronics, with this controller part. So much for this kind of high-level overview of quantum error correction. Let me now head towards the end of the presentation by describing, first of all, the global challenges and the impact in the last part of the talk of having quantum advantage. The global challenges that go beyond the technological challenges I was describing before are related, of course, to having to have an accelerated innovation cycle. So IBM, for instance, was mentioning that their innovation cycle is lasting 17 days from the day they have basically some low-tier level until the day they have a prototype and test an idea. We are also working in IQM to go towards this time scale, because it's very important to have very fast speed and test different solutions across the stack in parallel. But more important for the community is that we are able to reduce the cost per qubit. Why? Because currently, if you divide the number of the price of the systems that are being sold in the market by the number of qubits, this means that the price per qubit is currently tens of thousands of dollars, including, of course, the electronics cryogenic wiring. This is a very naive calculation where you just divide. But of course, if we are going to go to logarithmic scale, because we are going to go to this fault tolerance era, this means that we need to reduce at least 1 order of magnitude, but ideally more, in order to be able to keep the prices competitive and realistic. Of course, there are different reduction strategies that we have to play with: large scale production, efficiency in also technological level, in material use and cooling. But this is something that we need to work as a community. Maturity of the supply chain is going to be very important. Then the other global challenge is that we are able to increase the system production because, of course, one thing is that you are able to produce one system in a very artisanal way. And the other thing is whether you are able to produce more than a manifold of systems per year. And of course, the target in the number of systems that you need to produce will depend on the user scenarios. And let me maybe go to the last part of the talk, where I'm going to be describing a bit the applications and how are those impacting in the usage scenarios. So we all know that, in principle, quantum computers, they are gonna be useful for tackling problems intractable or that in classical computers are slower. And what we are working in our teams in IQM is on algorithms within 3 different classes that connect with multiple applications. Here I'm putting just a few examples in life sciences and also on operations. I think the key conclusion in this slide that I want to remark is that we are producing here kernels or quantum accelerator pieces that are going to be merged into workflows, for instance, in drug discovery processes. And you may be skeptical, like I was, on thinking whether this would be enough commercial impact. And the answer is apparently yes, because, for instance, there are examples like a company called Schrödinger that they are doing simulations for drug discovery. And they were able to produce a kernel that is based on QPUs that reduces the calculation of molecular dynamics from several weeks to a single night. And that already has created a lot of traction for this company. So here the goal is to do pretty much the same for these different algorithm classes. Let me maybe, for the energy part, I'm, by the way, a bit more skeptical. There is this idea that quantum computers can potentially solve similar problems as classical computers in an alternative way with potentially less consumption. I'm not going to be entering into this garden because I think this is not proven and it needs to be seen. How does this end up in the final calculations? There are also rebound effects, meaning that the more problems you are able to solve, the more you use the quantum computers and the more energy you are going to consume. So just a few words about this first class of problems that are, in principle, not easy to reach with classical computers. Like, for instance, the problem of describing batteries for optimization of their performance. So here we are dealing with a battery model where we are targeting this region, this electrolyte region, because it's core for increasing the battery performance and longevity. This region is containing electrons that are very strongly correlated, very entangled, and this makes it very hard to compute classically, this kind of dynamics or physics. So what the team of Fedor, Sinkovic, these are the 3 authors, did recently together with Volkswagen was actually to consider a hybrid flow, kind of a quantum-assisted quantum Monte Carlo model in which they were using quantum component that would calculate the first trial of the wave function describing the electrons within the electrolyte region. That was actually giving a hint to the classical part of the computation, this Monte Carlo sampling, to be able to avoid the regions which present a dynamical sign problem, which makes the sampling very slow. So, but just to recap a bit, what this means is that the quantum computer is going to be just a piece within a very large workflow. And this is exactly the piece that corresponds to the trial wave function. But if this piece is sufficiently fast, the idea is that when it's used in a workflow that calls this piece several times, for instance, to refine a model of a battery, then this produces a lot of impact. But let me just end my talk by recap and saying to you why are those 2 different aspects so relevant when it comes to my final reflection on how will quantum computers impact society and the market. So I think in the scenario that we have in the early years of quantum advantage, where we have actually very few systems being produced, we're going to be tackling problems that are hopefully having a high value, but requiring low-frequency quantum jobs. Like, for instance, coming up with a great blueprint for a battery material. The business case means that you need to be able to produce a lot of impact from a single or a few calculations with the quantum computer. And this would enable to get traction from a few systems per year. later on, when the maturity of the technology and the industry is higher, then we are going to be dealing with quantum computers being used massively, iteratively. We talk about kernel solutions for molecular material design, portfolio optimization, financial markets, modeling. And here we talk about multiple customers, cost amortized over many jobs. You don't need to create such a huge impact like here. And the target production is to have maybe hundreds of systems per year. With this, I would like to thank you for your attention. I think I ran out of time.
But we have still enough time for questions. So first of all, thanks a lot for the great talk.